Hi, everybody. Welcome to the session about DynamoDB transactions. My name is Edin Zulich. I'm a specialist SA focusing on NoSQL and DynamoDB. I also really enjoy transactions, well, in DynamoDB, not that they're out, but I also like serverless platform at AWS, and I'm very interested in how some of the databases and DynamoDB in particular work with serverless components of the platform and how we can use those to create serverless architectures. And I'm interested in solving problems that have to do with microservices in that context as well. Anyway, today the agenda is we're going to start with an introduction to the new transactional API in DynamoDB. We're also going to talk about ACID in DynamoDB. Then I'd like to focus a big part of this talk to use cases for which transactions make really good sense. And then some of the use cases, maybe edge use cases, where transactions API might not be the best choice. And finally, we're going to talk about things that I think you should know about transactions API. So let's kick it off with an overview of transactional API at a glance. Transactional API is request response. It's a non-conversational API. There is no begin-end transaction. You simply create a transactional request to either write or get items out of DynamoDB. Now, these requests can be customized with appropriate conditions that you want your state of the database to meet before you transition to a new state transactionally. Right? So transactional API for writing includes API for condition checks, and that's actually new. So what that means is you can create conditional checks on items that you need to check, but you're not going to transactionally update. And then you can also have checks on the same old PutItem, UpdateItem operations as part of that transaction. So it's really versatile and flexible and allows you to put together a transactional request, send a request as a synchronous operation, get a response back that's basically a success or a failure. For TransactGetItems works much the same way. You can get up to 10 items back, same as for TransactWriteItems API. The scope of these operations is any table, multiple tables in the same account within the same region. And I should also mention, if you're wondering, why is this request response style as opposed to the very common begin-end transaction? In the world of NoSQL, where we care about scale and performance at scale, this makes a lot more sense. Right? This is in keeping with the spirit of DynamoDB as a very scalable database that performs well at scale. And that's kind of one of the reasons why we have the limitation on 10 items per transaction. We feel that that's sufficient for most use cases out there. And also, I take that as a clue. If I'm thinking about transactional behavior, I know that the API is designed to only take 10 items at a time. And so if I'm looking at something that might go beyond that, that might not be a great use case either. So let's talk a little bit about ACID in DynamoDB. Before transactional APIs, we've had, obviously, these batch APIs, also single item APIs for a long time. And if you might be wondering, so single item operations have always been transactional. If you're doing a put item or update item, delete item, these operations are always all or nothing. You can't have partial updates to a DynamoDB item by way of any of these operations, right? And so transactional API extends this capability to multiple items and, if need be, across multiple tables. And then again, if you watch some of the reInvent talks, especially from Rick Houlihan, right, on advanced design patterns, he was the first one to point out, you know, the transactional API supports multiple tables, but you probably shouldn't be using it for transactions over multiple tables. There might be exceptional cases, but as a general rule, you should stay away from doing transactions across multiple tables. And we'll talk about some of those use cases. So back to this sort of little comparison of new transactional and the existing non-transactional and transactional APIs. So the new APIs extend the transactional capabilities to multiple items. So by contrast, the existing non-transactional APIs, and I think batch APIs in particular, do not have transactional semantics. They exist for a different purpose. They simply exist to make your interaction with the service more efficient. So you're loading data into a table, maybe you're migrating to DynamoDB or what have you, use the batch APIs. They're also limited in the sense that you can't have conditions on those writes or updates, right? They're just designed to be write only in batches. So when the service receives a batch, it applies all those operations as individual operations. And that's one of the main points of difference between the transactional APIs and the existing batch APIs. Worth noting that for also query and scan API, when you're doing a query, data that you're getting from DynamoDB might be updated by what else might be going on, single item operations or transactions, right? The thing to remember though, you will always be getting committed read state, right? You will never be getting data that's not committed, and that's what we call read committed, right? You can rest assured that your scan or query operations will always be returning committed state. However, that query as a whole, the result set isn't going to be serialized with respect to other operations that might be taking place. What that means is that the way I really think about that is when I execute a query, that's not just, oh, this is the state at a single point in time. Because query execution might take some time. You might be paginating through multiple pages of result sets. Well, DynamoDB does all that sort of on demand in real time. And so something else, other threads might be updating data as you're also reading them. But the key thing to remember is you will be always getting committed state of your data. So quick overview of ACID support in DynamoDB, atomicity, right? Isolation serializable with respect to other operations, single item or transactional operations. And then we'll talk a little bit more about that in a second. Durability, the same as always, right? Very durable DynamoDB. There is a support for idempotency, and that's a really helpful new feature. We'll talk a little bit about that in the coming slides. Synchronous, as I said, APIs, right? They do not, there's no blocking, in other words. There's no possibility of deadlocks with these either. And we'll get into that a little bit more as well. Condition checks are supported, right? These APIs are subject to the same availability of 4 nines within a region as everything else, right? They're designed for predictable performance and also to be scalable. Isolation between operations. You will see that between any and all transactional APIs, isolation is serializable, right? There's no interleaving possible. These operations occur as if they've been executed in a sequence. However, if you're looking at batch operations, especially batch write item, right? These are not serializable. But if you take each individual operation outside of the batch, those individual writes will have serializable isolation with everything else because they're just like any single operation or transactional operation in DynamoDB. Query and scan, as I mentioned earlier, read committed isolation, right? And then same for batch get item. So as far as durability in DynamoDB, you probably know this already, but when you write to DynamoDB, here's an example, order, and I'm obviously writing this to a table. What happens is that under the hood, this table might have many, many partitions, right? They're also split across 3 availability zones. And so when that put comes in, DynamoDB takes the partition key, creates a hash, and figures out which partitions will be written to, and makes basically 3 copies of your data. And that's true whether you use single or multi-item transactions, right? Every time you write, this is what happens. A minor detail to point out, 2 of these copies are done synchronously, and then you get acknowledgement of your write. So you're highly available, right? And then the third one, for performance reasons, is done asynchronously. Now, the beautiful thing about this isn't just the durability, because you have 3 copies and 3 solid-state disks. It's also that the service actually runs in 3 availability zones. So even if the whole availability zone becomes unavailable, you probably won't even notice, because the service will seamlessly basically just continue to run in the remaining 2 availability zones. Let's talk about use cases. I really wanted to get to use cases for transactions as quickly as possible. And so here's a sort of a sweet spot use case for transactional API. In gaming industry, our customers use DynamoDB to store game state for gamers, right? This is an example. We have partition key that's gamer tag, user ID. And then gamer state is essentially stored as a collection of items. That's not necessarily the only way, right? You could store the state for each user as a single item, and some people do. The difference between the two, if you use multiple items, gives you the ability to access and write with a finer granularity, right? For example, in this case, this application allows you to spend some of your assets, coins, to acquire more health, right? And I don't need to retrieve the entire state, the entire gamer state, basically, which might be fairly large, right? I mean, in some cases, we're talking dozens, hundreds of kilobytes. I don't necessarily want to do reads and writes of so much data, right, with every operation that I need to perform. So I can simply read the assets and status for this gamer. And of course, this is naturally a transactional operation. This gamer wants to buy more health. I need to transactionally essentially reduce the number of assets, coins, that's sufficient to acquire the amount of health that the gamer wants to do. So transactions is really provides you a good way of doing that. So this is sort of what the TransactItems looks like. We have 2 items. We have a condition, right? You have to have enough sufficient amount of coins, assets to do that. And then if these conditions are met, if they're all true, the transaction succeeds. And it's done in an all-or-nothing manner. It's ACID, right? And that's a really your basically typical example, right? Transactional API makes this much easier to do. Without transactional APIs, well, we have to either use client transaction library, or we have to have some kind of a lock mechanism of our own, but then we have to worry about all the edge conditions ourselves. So another example, let's say we're managing product inventory with a change log as well, right? So every time we, let's say, reduce the stock of a given product, we need to, well, first of all, insert the change log, subtract the amount, but also change the quantity on the top item, which has the sort key event ID of 0. That's a kind of a symbolic value. It represents the main state item record of this product, right? And so we see a list of change records. And so whether I'm subtracting or adding more stock to this product, I need to basically do that and update the stock level transactionally, right? And so transaction API is a really good way to do that. Not only that, but in a lot of cases, idempotency, right, is going to be a concern. I don't want to execute the same transaction twice, and the transaction APIs give me basically an option to do that as well, so that if the same transaction is, for whatever reason, executed more than once, it's not really going to be applied more than once, right? The service will recognize that, oh, this is just another attempt using the same idempotency token, so it'll read the record, but it won't basically apply changes. Another example that's very different is, people actually do migrate from relational database to DynamoDB. This is one example. In fact, it's from the DynamoDB user's guide. We're not going to go into too much detail of this example, but in this case, it's an order entry system that has a number of entities, right? Orders, customers, products. Also, employees that work with these orders are part of that system. And so several different updates in the system have to be made in a transactional manner. And so first, though, how do we design this in DynamoDB? All those entities, relationships, and so on. The basic design pattern, if you've heard Rick Houlihan speak, right, either at reInvent or elsewhere, he talks about adjacency lists. It's a now well-documented pattern in DynamoDB documentation as well. But it's about really modeling simple graphs of entities and relationships as an adjacency list. So in DynamoDB, what that means, entity will become a partition. So we'll use a partition key to basically store different entities. And the best part about it is they can all go into the same table. And then relationships to other entities are stored as using the sort key as the target, basically, edge for the relationship. So in this case, to support all these different access patterns, how do we look up an employee? How do we look up an order in various ways? The data model ends up looking like this. And how do we get to this model? We look at those query and access patterns, and we make sure that we have a way of modeling each access pattern using the data model. So this table is one way. It's going to model one side of each many-to-many relationship. But then in addition to this, we would end up creating global secondary indexes in order to model the reverse side of many-to-many relationships. We're not going to go into all the details of this, but I want to point out the use case for transactional API here. We have orders, and we have to enter all the order details transactionally, right? At the same time, we need to update the employee record who's working on that order because that employee carries a quota, the order changes the quota, and all that is a single transaction just naturally. And now we can do that using the transactional APIs. Another example that I wanted to talk about, use case that I think we're going to see sort of more and more of, is modeling transactions in microservices. Let's consider an e-commerce application. Probably has a lot more microservices than this, but this will do for the purposes of this example. Here, we're dealing with a shopping cart service, product inventory service, there's account service. One basic thing about microservices is that they're isolated from each other. They're decoupled from each other, right? What that means is each one is bounded by its business context, and that applies to data. Each microservice owns its data. Other microservices should not be accessing the data that belongs to other microservices directly, only by invoking APIs, right? So you can imagine in this kind of application that we obviously need to make transactional changes to the shopping cart. We need to make transactional changes to the product inventory, much like in one of the previous examples. But we also might need to make transactional updates that span these microservices. Let's start with just and before that, in fact, I wanted to just point out, you know, a sidebar. This is something that you can actually implement using serverless platform at AWS, right? If you're talking microservices, API gateway becomes a natural place to define your microservice APIs. Lambda provides obviously the ability to implement your compute, all the functions that basically you need for your microservice in a single place. And then DynamoDB, in fact, if you didn't know, is the only database that's part of the servlet platform that's essentially eligible for both PII and HIPAA data, right? So these services make a compelling case for looking at how to develop your applications, greenfield applications, as, let's say, serverless microservices, right? Using the serverless platform. So anyway, The first thing we want to look at is shopping cart service and how we represent data in the shopping cart. In a relational world, we could imagine a couple of tables, cart table, cart item, and then we have to do joins and so on. In a non-relational world, we want to think in aggregates. Shopping cart is a collection of related objects that we always write and read together because that's what makes sense for our application. I can model that using a single table very easily. I can model that as a single item in a table. I can also model that as multiple items. I can see, for example, how someone might design this data model such that you have a separate DynamoDB item for each product in a shopping cart. And that would give you the kind of granularity that allows you to access each item individually, whether you want to remove it from the cart or update the quantity and so on. Both options are perfectly valid, and which one you go for may depend on other requirements that you have in your application, right? So the main point of difference that in a relational world, we would have a fully normalized schema. In the non-relational world with DynamoDB in particular, we would want denormalized schema, right? Using a single table to store the data. And so how do we do updates to this cart in a way that's consistent? And by the way, data consistency in this context does not mean strong consistency, eventual consistency. It means logical consistency of your data. It means I start with an empty cart, I put a TV in it, and when I view, I see a TV in it. I don't see a refrigerator in it, right? Or I don't see an empty cart, right? And sure, in this kind of use case, it's normal that each user would have their own account, their own shopping cart, and so on. But we all know people who have an Amazon account and they share it with family members, right? So I'm going shopping and I happen to share my account with Uncle Bob and he's buying a refrigerator, I'm buying a TV, right? And so if I don't have data consistency, we might be seeing weird things, right? Uncle Bob might end up seeing my TV in the shopping cart but not his refrigerator, and so on. So how do we implement these updates in a way that are consistent, right? And those state transitions happen, but they always end up in a consistent state. So we do have to read the cart data, and so we use GetItem API. Now you might be wondering, should this be eventually consistent or a strongly consistent call? And I'm going to let you kind of sit on that thought and think about it for a moment as we step through the process here. So we make changes in the shopping cart service, right? We add our TV set. Now we need to update the cart. And what do? Well, it's the conditional PutItem. It's the condition expression that gives us the ability to do this in a way that's going to ensure that consistency. If we start with a cart and we have a, let's say, version attribute, we're going to read that version attribute, and we're only going to update the cart if that version attribute matches what we read. If it doesn't match, it means that something else has updated the cart, and we need to abort. And what do we do if we abort? We basically need to reread the item. We need to get the most current state. So this is the optimistic concurrency control. But you'll notice that whether we do that get item in an eventually or strongly consistent way does not really matter in terms of correctness. If I do a strongly consistent read on that get item call, yeah, okay, I'm going to get that consistent state. I know that that will be the state at the time of the read. Eventually consistent call might result in a stale state, but what's the worst thing that can happen? My conditional update will fail, and I will have to reread the state and redo it. But there's nothing wrong with the logic or the algorithm itself, right? I might have an extra read and an operation to do, but that's about it. So the point is, we use conditions to implement optimistic concurrency control. And as you'll notice, I'm not using new transactional API. Why? Because the single item API is just as transactional when I'm working with a single item. If this were a multi-item collection, I would have to use the new transactional API. So I just kind of wanted to point that basically out and sort of compare the two. For this use case, it's perfectly, in fact, you do want to use a single item API because it's also cheaper. I mean, sure, you could end up using, you could choose to use the new transaction API, but you really don't need to. Now the question that we need to answer next is, how do we do transactions that span microservices, right? So imagine a situation where shopping cart is ready to be checked out. The customer clicks the checkout button, but now we have to update the product inventory, and we should actually do that in a transactional way, right? We need to make sure that cart and items that are in the cart are available in the product inventory. So the traditional approach is, I have a big old transaction, and I have some kind of transaction manager, and I just do that transactionally between the two. But that breaks, that violates one of the basic microservices design tenets, right? That these microservices should be decoupled. If I do that, they're not decoupled anymore. And so this is one of those cases, where new transaction API could easily do this, right? But should you really do it using the new transaction API? Well, the problem is, again, coupling of those two microservices using that transactional API. So this is where we really want to apply caution and think about this twice. And if we're compelled to say, well, heck, but it's a lot easier to do this with the new transactional API, which, by the way, it is, right? Then we have to make the case of combining these two microservices into a single microservice, right? And so that's the sort of, I think the process there. So what can we do differently, alternatively, right? We could implement this as an eventually consistent sequence of transactional events, so that in the end, we have a consistent state between the two or more microservices, right? How do we do that? Well, if we're using DynamoDB for this, and especially if we're building this as a serverless application, so now we have Lambda in the game where our business logic lives, we can take advantage of the two. The two represent a very powerful building block for reliable event delivery of events, right? So if I have DynamoDB streams, I'm going to take it that you're all familiar with DynamoDB streams, and I turn that on for my card table. All the updates to the card table are now reliably delivered by the DynamoDB stream. I can have a Lambda function, in this case. It could be your own application, right, that subscribes to the stream updates as well. But serverless is a lot easier and more fun. Lambda really integrates well with DynamoDB streams. And so what I have now is a reliable event delivery mechanism. DynamoDB streams will deliver events exactly once. However, a Lambda function could be executed more than once on the same event. So this becomes a reliable, at least once, event delivery mechanism. So what does that mean? So in case of Lambda, idempotency becomes very, very important when you hook up Lambda to a DynamoDB stream or a Kinesis stream. And so this is now where we can take advantage of the new transactional API that provides idempotency features to do this much easier, in fact, than before, right? So in this case, I can imagine a checkout event. It's just an attribute on my shopping cart table coming through down the stream. In my function, I basically see that, oh, checkout is true. I need to update my product inventory table. I need to make sure that I have inventory for the items that are in the table. And if that's true, I can actually use transactional API to do that because it gives me idempotency. It also because I have multiple items in the shopping cart, I have to use a transactional API. But it's a win-win situation, right? I have idempotency feature that's really helpful, and I can use the transactional API to update the product inventory. If it all goes well, I just need to invoke commit API on my shopping cart service and finish it off, or move on to the next step, charge the customer account, or what have you. So this pattern is a choreography. It's a saga pattern, right? So a saga pattern is an eventually consistent sequence of events that amounts to a distributed transaction. And we really use and depend on DynamoDB streams and Lambda to do that here. So the table, product inventory table, it's basically that same example that I showed earlier, but we can update the state for each product. Of course, in this case, we might have multiple products, and this can all be done as a single transaction. We can use the item potency feature and take care of that. So finally, let's not forget one other thing that we need to do. We need to provide a rollback API, right, for these distributed choreographed transactions, right? Because should there be a failure to check out or to basically find sufficient inventory for our transaction, I need to invoke the rollback mechanism on my checkout table and basically cancel the distributed transaction, if you will. So all that means is that I need to basically change that state of my cart back to before checkout. Maybe there is a failure message that I need to somehow display to the customer as well. So there are benefits and drawbacks to this approach. The key benefit is that we're keeping our microservices still decoupled, separate from each other. One of the main drawbacks is it does kind of complicate how we do transactions between multiple microservices. But one really nice thing about it is you can take advantage of DynamoDB streams and AWS Lambda to help you with this. And there's something else I wanted to say, but anyway, it escapes me right now. It doesn't matter. So all these features basically are designed to support use cases that we just talked about. Item potency token, right? So condition checks, right? We need these things to effectively implement transactional behavior. And as it turns out, we really don't need that conversational semantics of a session begin-end. We can do this more effectively using request response APIs. Next, I'd like to talk about things to know: concurrency control, cost. How do we deal with failures with transactional APIs? So first, when a single transaction, the condition check is also part of that new API that's completely new with transaction API and applies in the context of TransactWriteItems, right? You can have condition checks, you can have operations that update items. In all, you can have up to 10 operations between condition checks and update operations. One limitation is you can't update the same item. You can't have the same item in multiple operations, including condition checks. So the idea behind the condition check is I need to check some part of state that's separate from the items that I need to update. But then if that check succeeds, I'm going to update different items, right? If the check is related to the items that I need to update, you can just use existing condition expressions. And so, again, point of difference with batch write item, which do not allow condition expressions. Concurrency control is optimistic, right? So we also saw optimistic concurrency control in the shopping cart example. That's the world of NoSQL. These are the sweet spot sort of types of use cases. I can have a huge number of concurrent users, but chances are they're all operating on their own data. So all these transactions, updates can go basically in parallel without stepping on each other, right? Because in case of a shopping cart, every user, I can have millions of users on Prime Day, Cyber Monday, Black Friday, what have you, and they're all using their own shopping carts. There's no contention on rights. And that's where optimistic concurrency control makes a lot of sense. In addition, the transactional APIs are implemented in a way that deadlocks are not possible. However, there is one problem that you can run into, and that's if your contention of rights goes up, right? So if conflicts become possible, then you could have failing transactions due to conflicts, right? And transactions could be canceled if you end up executing multiple transactions on the same data, basically, right? And so that's another reason to keep those transactions small, avoid unnecessary conflicts designed for scale out by limiting the scope of your transactions to the basically scope that's required, that's needed, but nothing more. And this really goes back with the design principles of DynamoDB that have to do with low latency and the ability to scale out. Cost, metering. So when you perform transactions, the cost, if you're doing TransactWriteItems, and let's say you have 10 items, 10 writes, you add up all the write capacity, and then it's going to be times 2. There's a write basically to prepare, and then another write to commit a transaction that the service needs to do on your behalf, right? The good news is you don't have to worry about it, but the service still has to go through these steps. It's all automatic, but you will see an increased cost, double the cost, right? DAX also, which now, by the way, supports transactions since reInvent, that's a new feature, right? Will incur additional read costs because it'll use TransactGetItems to read items from DynamoDB before it updates the cache. So just pay attention to that, right? Failure conditions. Things can fail. Things can fail for the same old reason that other operations can fail. But also, transactions can fail due to transactional conflicts, right? And those conflicts can be with other concurrent transactions. They can also be with other single item operations, which are transactional with respect to a single item. And in fact, in that context, single item operations now also have a new exception, transaction conflict exception, right? So if you're adding transactions to your existing application, there is a new exception that you might basically get with your existing single operations, and that's a transaction conflict exception. If there is a transaction in progress that's updating, let's say, item X, and another single item operations tries to update the same item while the transaction is updating it, the single item operation will fail with the transaction conflict exception. So a quick note about ClientRequestToken, idempotency, right? SDKs provide this option automatically. You can also customize it. In other words, provide your own idempotency token. And so idempotency token is good for 10 minutes, during which, if the same transaction is repeated, it will not be executed. The service will recognize, based on the idempotency token, that it's the same transaction. However, if you do change any part of that transaction, you're going to get a different failure. You're going to get an idempotency parameter mismatch failure, which will tell you, oh, hey, look, you use the same idempotency token, but this is now, the contents of this transaction is different, so it's a different failure. So in case of failure, right, so there are retries that the SDK will do for you, for example, for idempotency, transaction in progress, but then there will be failures that you have to handle. Transactional conflicts, right? And so what do? Much like with the single item transaction, you have to reread the state, right? And then there's 2 or 3 ways you can do that, right? You can set the option return values and condition check failure, all old, so that on the failure you actually get the current state that's committed, and you can use that to rebuild your transaction. Or you could do you could carry out any number of read operations, right, that are available to reread the state and recreate that transaction and execute it again. Access control, same as always. One addition is new control for condition check. But other than that, you have to have permissions to perform all the operations that are part of the transaction in order for that transaction to succeed. As far as interaction with other DynamoDB features, First of all, and you've heard me say this earlier in the talk as well, you can only at any point in time read committed state from DynamoDB, right? So you're safe. You're not going to get some wacko state that just isn't committed or that's some kind of hodgepodge, right? The state is always read committed, right? But DynamoDB is a distributed system, right? And so the scope of transactions is limited to basically some of these features. So it does not extend to streams. What it means, the data that's coming down a stream, you could see committed data, but not necessarily entire transactional set. And again, you will always be getting committed data. So same with backup restore, GSIs, right? These are all updated in the same old fashion. As the data is committed, those updates are propagated. Global tables, in fact, very important to know that when you create a global table, transactions are automatically disabled just because replication for global tables is not transactional, same as these other features. So you can opt to request basically to have global tables and transactions coexist, but you still cannot basically get transactional behavior across global tables. And finally, DAX support. DAX now supports transactions. That's new since reInvent. TransactWriteItems will write through DAX. TransactGetItems will simply also pass through, forward the GET request to DynamoDB. The support is implemented in Java, Node, and Go SDKs. Soon to come is the support in Python and .NET. That's the plan. Again, not a promise, but that's the plan. There is a note about additional reads, as I mentioned earlier, right, when we talked about metering and cost. With DAX, when you do TransactWriteItems, DAX will also invoke TransactGetItem for each item separately that's part of that TransactWriteItem in order to update its own, populate the cache, right? So that'll incur extra reads, right? Two times of reads for each basically item, right, that was in the write transaction. So this is all also well documented. If this doesn't make sense or if you need a reminder, I will actually have links to the documentation at the end. So to wrap it all up, best practices, right? As always, follow the good design practices, right? Design for scale. Make sure you don't have hotkeys, hotspots. A lot of times not possible. But it's important that even if you know, well, I might have hotkeys, hotspots, that you identify those use cases, and then you have a design option to support that, right? Avoiding contention of rights is also one of the key tenets with scalable design for NoSQL databases. But that said, you have to deal with conflicts, right, with exceptions and those edge cases. Avoiding multi-table transactions. The support is there, and there are cases in which it might make sense. But as a general rule, right, if you're looking at a design that involves transactions across multiple tables, step back and reconsider, right? Is this a good design, or is this a design smell, an anti-pattern? And limiting transaction scope, right? For liveliness, you reduce the chances of transactional conflicts, you reduce the latency, and you increase the throughput as well. Check out some of these links. For those of you who are here, you will have the ability to get the decks after you complete the surveys, and that's why I have these links. We do have a few minutes for questions. Okay. Request to go back to this slide. So please, any questions? And I know it's close to lunchtime, so I perfectly understand if you we can wrap it up a few minutes early so that you can go and get your food. But I will hang out here for a few minutes as well. If anybody would like to talk about any of these things that we covered in this talk. Oh, here's a question. Okay, so the question is, what is the reason you don't recommend multi-table transactions, right? It's the same reason why we don't recommend multi-table design in the first place, right? And that's simply because in multi-table design, you're just not as efficient, right? When you read or write, you're actually making requests to multiple nodes. In a single table design, when you have a partition key, you'll notice DynamoDB API, if you want to do a query operation, get item, put item operation, you have to provide a partition key. You know what that means is that you're interacting with a single node in the back end, which is an efficient way to do it. Go ahead.
Once you add global secondary indexes, are you effectively communicating with multiples again?
Yes. So the question is, once you add global secondary indexes, you're effectively now interacting with, yes. But the way to think about that is a global secondary index is just another materialized view that you need. 1, 2. The way we want to interact with a global secondary index is that when we query, we ideally only query the global secondary index. So we're still interacting with a single node if we do this right? Because we're projecting values that we want to query on. So unlike relational indexes that only contain essentially reference back to the main table, with DynamoDB, if you query a GSI, you shouldn't need to query the main table, right? Because with DynamoDB, you can project all the attributes that you need. So if you look at a query and you say, I need to project everything because I'm going to essentially query everything, one of the principles of NoSQL is we make multiple copies of data. And that's OK. That part of the denormalization is, we're going to have denormalized schema, multiple copies, and we're going to project what we need to that GSI so that we only need to query the GSI itself and not the table. Yeah, so you're right. Writes will have to basically be duplicated, but they're also duplicated for you, right? You don't have to do it. And that's done asynchronously as well, right? And that's kind of the main reason to have it basically done in an asynchronous manner is to protect that low latency of your writes, to the main table. All right. And it might be just time to have lunch, right? Thank you all so much. Take care.